Okay, our warm-up today was the workbook, page 426. And take a look at 1 through 4 and see if you have any questions about 1 through 4. Yes, sir?
Why is number 2 not the entire thing? Isn't that a union of A and B, so wouldn't that be all of them?
Okay, let me take a look at that one.
A and B don't equal 10. A and B together equals 10. Because there's 5. There's 4.
Oh,
There's 5.
I thought it was like that.
Why did you give me the number 10? So cool.
Are you good now?
Yeah.
Okay.
I didn't read it. I saw 10. I was like, oh, 10.
Okay.
I did a lot.
All right, any other questions about 1 through 4?
How did you get 36?
Okay, so event A is rolling a 1 on both cubes, and event A is the probability of event A occurring only happens once. You only get snake eyes once out of the 36 possibilities.
Oh.
So the complement of A would be 1 minus that, which is the 35 over 36. Does that make sense?
Yes, ma'am.
Okay. All right, let's take a look at these. Number 7. Okay, anything else? Okay, so number 7 says set J contains negative pi, square root of 2, 1, 0, and 1. Set Q is the set of all rational numbers. Which set represents the intersection? So the intersection are those numbers that are contained in both. So it has to be in both J and Q. Which ones are in both? Well, is negative pi, is that rational? No. So this one is not in both. Is square root of 2 rational? Nope. This one's also irrational. Is 0 rational? Yes. And is 1 rational? Yes. So those are the 2 things that are in the intersection. Okay? So it means they're in both. Yes, sir?
Can I get my phone to take a picture of something in my workbook?
In a moment. Okay? Are we good on 8?
Can you do it?
Sure. Okay, so number 8 says if you have 2 sets, A and B, and A intersect B have the exact same elements, and A intersect B have the exact same elements, what must be true? Well, that means the only element in A, or the multiple elements in A, are also in B if they're in the intersection. So I just did an example here. So here's B. B contains 1, 2, 5, and 7. And A contains 5. So here it states that A and the intersection of A and B have the exact same elements. So this picture does it. I could also put like another number, 3. So 3 and 5 are in A, but they're also in the intersection. Does that make sense? It says that A and the intersection of A and B have the exact same elements. So all of the elements of A are also contained in B. So I had to make a Venn diagram so I could figure it out. Okay, so the null set, someone asked about that. Null set is the same as the empty set. All right. Okay, let's take a look at your workbook from last night. I think it was 425.
For number 10, did you mean 0.7?
It's not on this page. It's on the next page. Can't see all of it.
How do you get 9 out of
There's
10?
10. We'll go there. Okay. What?
How do you get 9 out of 10 number 6?
Okay. In this one, union means everything in one or the other. Can be in either one of them. Okay, so set A is drawing a tile with a vowel on it. So our vowels are A, E, I, O, and U. And then B is these. So I already have A. Now I add B. I don't have C, so I add that. I don't have D, so I add that. I already have E, so I add F. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 out of how many letters are there in the alphabet? Okay, any other questions on 1 through 9? Okay, here are 10 through 14. Okay, any other questions about 10 through 14? Yes, sir.
14.
Okay, what else? Okay. So, 14 says, give an example of two sets A and B, for which A and a union of A and B both contain the exact same elements. Okay, so all you have to do is make A contain everything that's in B. So you're making B a subset of A. A probability and the probability of its complement always add up to 1. So if they give you 1, you can subtract it from 1 to find the other. Okay. That subset thing would work for this too, wouldn't it? This means that A has to be a subset of B, doesn't it? That all the elements of A are contained in B on this problem too. So they gave us 2 where we had one that was a subset of another. Okay, bookwork. Now we have drawn out some sample spaces for you here so you can see them. Tree diagram and a table. So sometimes you need to see your sample space. all 4. Did you draw out your sample space for this one? Okay, so on these problems it says a quarter, a nickel, and a penny are flipped. Find the probability of each of the following. Okay, so the quarter shows heads. So we have a quarter, a nickel, and a penny. If we look at our entire sample space, our quarter can either be heads or tails, right? And then we flip our nickel, so it could be heads or tails. And then we flip our penny, so it could be heads or tails. Or if we had gotten a nickel here, heads or tails. So the first question is just dealing with the quarter. What is the probability that the quarter shows heads? Now we don't even have to look at our entire sample space, you can just think about a quarter. How many sides of the quarter are heads? 1. Out of how many sides are there? 2. But if we even looked at our entire sample space, there are 8 possible outcomes when we flip all 3 coins. Does the tree diagram make sense? Okay, so there are 8 possible outcomes, and do you see that 4 of these possible outcomes had a quarter on heads? So 4 out of 8 reduces to 1/2. Okay, let's take a look at number 3. Number 3 says the penny and the nickel show heads. So if we had the penny and the nickel showing heads, the penny and the nickel show heads here. So that's one case. And the penny and the nickel show heads here. So 2 cases out of the 8 possibilities have a penny and a nickel with heads. 2 eighths, which is 1/4. Does that make sense? Okay? All right. Number 4. 1 coin shows heads. All right, so only 1 coin showing heads. So this is heads, heads, so that eliminates all of that. This is heads, tails, tails. So that's 1 possibility, right? Okay, so this is tails, heads, heads. And we only want 1, so this is tails, head, tails. That works. We got 1 head. And this is tails, tails, heads. This one works. Because that's all tails. So 1, 2, 3 out of the 8. Does that make sense?
Yes.
Isn't it a lot easier when you're actually looking at your sample space? Okay, so we could look at it 2 ways. It's drawn out here as a tree diagram. It's drawn out here as a table. And if we look at it in the table, do you see 1 head, 1 head, 1 head? There are 3 out of the 8 where there's 1 head. You can look at it either way. Whichever way is best for you. Are you guys good with 5? Okay. Any questions about 6 or 7? All right. So here's 8. Through 13. Take a look at those first and see if you have any questions for me. 8 through 13. 10 and 11. Okay, number 10 and 11 are both talking about a picture we can't see right now. So, let me see if I can snip that picture so we can talk about it. No, that page does exist.
Yeah.
Okay, so now we have our picture to look at that goes with 10 and 11. So, in number 10, it says, we're supposed to find the probability that a point chosen at random is in the shaded region. So what we had to do was find the area of the shaded region over the area of the entire target. So to get just the shaded region, do you see you need to do the medium circle minus the small circle? Gives you the shaded region. And area is pi r squared. So the small circle, it has a diameter of 4, so its radius would be 2. And the medium circle would be 2 and 2 more, so it would have a radius of 4. So that's where we get the 16 pi minus the 4 pi. So the area of the shaded region is 12 pi. Over the large circle, which is our total, and the large circle would be the 2 and the 2 more and the 2 more, so it would have a area of pi times 6 squared, or 36 pi. So the pi's are going to cancel, and 12 over 36 reduces to 1/3. Now number 11 says that the point chosen at random is in the smallest circle. So this one's actually easier. We know that the area of the small circle is 4 pi, and the area of the larger circle is 36 pi, so it reduces to 1/9. 4 over 36 reduces to 1/9.
Okay, so two numbers you're dividing for 10, it's the area of
The medium circle,
over the bar.
take away that part.
Okay.
That gives us just the shaded region.
Okay.
Okay? All right, let's keep going. Here's 14 through 20.
What? 20 down 4.
Good job, Chris.
I think it's on the next page. Number 17. Okay, number 17 says a coach randomly selects 3 swimmers from a team of 8 to swim in a heat. What is the probability that she will choose the 3 strongest swimmers? Okay, so we're choosing 3 out of the 8. And we want the 3 strongest. So if there's 3 strongest for that first one, what is our chance of pulling one of those 3? 3 out of 8. Then we pulled the strongest. And we pulled 1. So then it is 2 out of 7. Then 1 out of 6. Does that make sense? Okay. Yes, ma'am.
Number 20.
Number 20. Okay, on number 20, the question reads, an experiment consists of choosing one card from a standard deck of cards and then replacing it. The experiment was done several times. The results are 8 hearts, 8 diamonds, 6 spades, and 6 clubs. What is the experimental probability that the card is red? Okay, so how many red cards did we choose? Well, hearts and diamonds are both red. So 8 plus 8 gives us the 16. Out of how many total times did we perform this experiment? How many trials were there? Well, we would add the 8 plus the 8 plus the 6 plus the 6. And so our total is the 28. So our experimental probability is 4/7. What is our theoretical probability of choosing a red card?
415.
How many cards in a deck are red? Half of them. So our experimental, does it always equal our theoretical? No.
It's sometimes.
Sometimes it does, and the more trials we perform, the closer it gets. Right. The greater the number of trials, the closer it'll grow to our theoretical. Okay, so there's 20 finished for us, and here's 21 and 22. Word after probability.
Okay.
Yeah, that's PROB is the way math teachers abbreviate probability. What now? Okay. Today we're going to look at two types of events that can occur. Independent events and dependent events. So today we're just going to look at them, we're going to talk about them, we're going to work some problems, and then tomorrow we're going to go back and prove. How can you prove events are independent? How can you prove they're not independent or that they're dependent? How would you prove that? So today we're just going to learn basic definitions and we're going to work problems. So that tomorrow when we look at the proof part, which looks a little more theoretical, looks like math symbolism, it won't be overwhelming because you'll understand. You will have worked with it. You'll know what some of the terminology means. So we're going to flip on over and do some notes from our workbook. And you're going to notice I'm going to skip. And I'm skipping on purpose because today we're skipping the proof part. The proof part can become overwhelming if you try to do it at first. Yes, sir.
Oh, are you recording or being recorded?
What page is that?
Go.
This is the next page. So, well, no, it's 441. 441. It is not the next page. It is page 441. Lesson 19.1. So today we will be answering this essential question, which I should have changed on my board. How do you find the probability of independent and dependent events? So today we're actually finding the probability, and tomorrow we're showing how to prove. All right, so the first thing we see is the definition of independent events. So that's too hard to see through. Two events are independent if the occurrence of one, y'all just underline that because it's hard to see, does not affect the occurrence of others. So two events are independent if the occurrence of one does not affect the occurrence of the other. And then they give us an example. example, rolling a 1 on a number cube and choosing an ace at random from a deck of cards. Those are independent events. Because rolling the 1 on the number cube, does that have anything to do with pulling the ace out of the deck of cards?
No.
No. They are independent events. One does not affect the other. Okay, so we are going to skip from this important part right here. We're going to come back to this tomorrow because this is the proving. We're going to skip over to the next page, up at the top. It shows us that we can use a tree diagram to help us understand the formula for probability, and they'll give us that in a second. The probability of independent events. For example, consider tossing a coin 2 times. And we drew that sample space on our answer key last night, didn't we? We drew the tossing the coin, the quarter, the nickel, and the penny. So we've already seen a tree diagram similar to this, but this is tossing a quarter 2 times. So, the first toss, the probability of heads is 1/2, and the probability of tails is 1/2. And then on the second toss, the probability of heads is 1/2, tails is 1/2, heads is 1/2, tails is 1/2. The tree diagram shows the probability of the coin landing on heads up on both tosses is 1/4, because heads followed by heads is 1 out of the 1, 2, 3, 4 possibilities, right? It's 1/4. And this is because we have equally likely outcomes. The probability is simply the product of the probabilities. 1/2 times 1/2 is 1/4. Do you see how those match up? Okay? So, we had 1, 2, 3, 4 possibilities, and only one of them had heads followed by heads. So that's 1 out of 4. Or, we can go to this definition. If A and B are independent events, then the probability of A and B occurring is the probability of A times the probability of B. Did this work? Did we have 1/4 equal to 1/2 times 1/2? Yeah. So what we're going to do is we're going to take those probabilities and multiply them to find the probability of A and B occurring. Okay. Let's look at example 2. It says you spin the spinner at the right 2 times. What is the probability that you spin an even number on the first spin, followed by an odd number on the second spin? So let's just think about it for a second. Does spinning an even number on the first spin affect what I spin on the second spin at all?
No.
No. So we're thinking independent. Tomorrow we will prove, but right now we're thinking independent. So when we think independent, we'll find the probability of the first thing happening. So the first thing was spinning an even number. Please count the even numbers. How many even numbers are there on this spinner? 3. Out of how many numbers were there? 8. Now we want an odd number, so if there were 3 even, how many were odd? 5 out of 8. So the probability of spinning an even followed by an odd, an even and an odd, would be the 3/8 times the 5/8. So that probability would be 15/64. And so the probability that you spin an even number on the first spin followed by an odd number on the second spin is just that, 15/64. Okay, make sense? All right. Top of the next page. It just reiterates this, that events A and B are independent if this is true. And let's look, we're going to save this example for tomorrow because this is the proof. And we're going to flip over to example 4 now. This is where it talks about dependent events. two events are dependent if the occurrence of one event does affect the occurrence of the other. So we can really read and think about this and decide independent or dependent today, and tomorrow we'll come back and prove. So it says, suppose you have a bag containing 2 blue marbles and 2 black marbles. You choose a marble without looking and put it aside, and then choose a second marble. Consider the following events. Event A is the first marble that you choose is blue. And event B is the second marble you choose is black. Events A and B are dependent of each other because the marble that you choose for your first pick changes the sample space for your second pick. My first pick changes it for my second pick. Does that make sense? Therefore, the occurrence of A affects the probability of event B happening. So we have moved from what we were just looking at, independent events, into these are dependent events. And when we find the probability for dependent events, our formula is changed. For dependent events, we want to find the probability that A and B occurred. We do the probability of A, and then this reads the probability of B given that A has already happened. So it's the probability of A times the probability of B given that A occurred. And that is called a conditional probability.
Will you send the formula or whatever up to the first one?
Sure. If we look at the first one, this is event A. So what is the probability of choosing a blue?
1/2.
1/2. It's 2 out of 4 or 1/2. But when we look at this, we're doing the probability of A times the probability of B given that A has occurred. So this was 1/2, but now I pulled a marble and I didn't put it back. So now how many marbles are left? 3. And how many are black?
2.
2.
Okay.
So, but this is on the condition that I first pulled a blue. So my conditional probability would be 1/3.
Okay.
Wait, how would it be?
You multiply these two probabilities. The probability of A and then the probability of B given that A has occurred. It makes sense?
Yes.
Yes. Okay. So now let's flip over to page, there it is, 446. Number 3, a basket contains 6 bottles of apple juice and 8 bottles of grape juice. You can choose a bottle without looking, put it aside, and then choose another bottle. What is the probability that you choose a bottle of apple juice followed by a bottle of grape juice? In your head, every time you're asking yourself the question, does the probability of the first event affect the second?
Yeah.
If it says yes, then it is a conditional probability because these are dependent events. Okay? So now let's look at what is the probability of, what did it say first? That you choose a bottle of apple juice. So the probability of A choosing apple juice would be, how many apple juices are there? 6 out of how many bottles are in the cooler?
3 7s.
14. You're right, 3 7s. Okay, now, because it's dependent, when we look at followed by grape juice, how many grape juice bottles are still in the cooler? 8 out of how many bottles are still in the cooler? 13. Okay, so this reduced to 3/7. So this would give us 24 over 91. Does that make sense? Yes. Okay. Let's look at the next one. You have a set of 10 cards that are numbered 1 through 10. You shuffle the cards and choose a card at random. You put the card aside and choose another card. What is the probability that you choose an even number followed by an odd number? Independent or dependent? Dependent. Because we pulled the card out and didn't put it back in. So this is where, when you're looking at some of these games of chance, is there replacement? Because if we replace it, then they should be independent. Or did we not replace the card? Did we pull it out? Which makes them dependent. Okay. Is my bell about to ring?
Yeah.
Aw. Okay. I saw y'all moving. I did not get near as much time as I wanted to today. But you can go grab your phones. And I think we've done enough to understand most of your homework.